All right, this is part one of power amplifiers. So what we want to do is we want to get some definitions down initially. So we're going to talk about different output stages and power amplifiers. I'll just abbreviate power amplifiers as amps. Okay. Since the output stage is the final stage, of an amp, okay, it usually deals with relatively large signals. So the small signal approximations we've been using up to this point in this course and in this book, actually, the content you talked about last semester, was all small signal stuff. So those approximations, and they are all approximations for the most part, it may not work very good. So basically the measure of goodness when it comes to an amplifier, that's a technical term, goodness. Okay, we can say of output is the amount of total harmonic distortion. Maybe you've heard this term before. Total harmonic distortion, or THD, is what you'll see it abbreviated at typically. So the measure of goodness of output is the amount of total harmonic distortion it introduces. And this is an important thing to remember, and it makes sense. Okay, the smaller the THD, the better. All right. So let's talk specifically now about power amps. Okay, they're large signal amplifiers by definition. Okay, and what that means, we talked about low lines, and you talked about them last semester too. A much larger portion of the load line is used during signal operation. Than in a small signal amplifier. We'll talk more about what this means as we get into this chapter a little more. 4 basic classes that we'll talk about. Class A, Class B, Class AB, and we'll also talk about Class C. And these classes are based on the percentage of the input cycle for which the amp operates in its linear region. This statement may not make sense initially, but by the time we finish the end of this chapter, it'll make perfect sense. Let me add a new page. All right. So each class has a unique circuit configuration. Okay, so it's normally used as the final stage of things like a communications receiver. Could be a transmitter to provide signal power to speakers. Could be a transmitting antenna. So they're unique. Each is unique, and we'll look at some examples. So to start off, let's look at Class A. Class A power amps. Okay, so we said we've looked at small signal amplifiers so far in this class. In a small signal amplifier, the AC signal moves over a small percentage of the total AC load line. Now, when the output signal is large and approaches the limits of the AC load line, that's when the amplifier is considered a large signal type. Okay, both large, this is interesting, both large signal and small signal amps are considered to be Class A. So to be Class A, if they operate in the linear region at all times. Okay, so what that means, we can just draw a little, we can represent our amplifier here. It's just a triangle. Okay, this is AV, so it's a voltage amplifier. We got V in, we got V out. So we got a signal going in, signal coming out. I'll draw my signals in red. Little signal going in, amplified signal coming out. Okay, so we're amplifying voltage. We're not changing frequency. Frequency remains the same. We've got an input voltage, small input voltage, and a larger output voltage, let's say. Okay, there's no distortion, there's no clipping. Basically, you've got a sine wave that's at a higher amplitude coming out than what was put in. All right, there's some things we need to consider. Anytime you hear the word power, you really need to think about heat. So we want to talk a little bit about heat dissipation now. Okay. Anything, like I said, anything power related, any kind of power device, let's say, has to dissipate typically large amounts of heat. So for bipolar junction power transistors, okay, the collector terminal in particular is a critical, and we'll see why, again, critical junction. And for this reason, the transistor case is always connected to the collector terminal. To the collector terminal. Okay, the cases are designed, and I know you've seen them in lab, but they're designed to provide a large contact area between it and an external heat sink. In very high power applications, you get up over 300 watts or so. You'll see a cooling fan added. So heat dissipation is real important. You don't want the components themselves to burn out. You don't want to produce a lot of heat that could cook some of the other things that are close by. Now, let's talk a little bit about cue point. Okay. You recall centered cue point. And I'm going to draw, let's see, I'm going to draw a little curve here. Sorry. Okay, we've got IC, we've got VCE. If you remember, we're talking a bipolar junction transistor here. So let's just draw one over here. Okay, we've got base, collector, emitter. Okay, we've got a current here, IC, and we've got a voltage drop, or voltage difference between the collector and the emitter. So, if you remember from your from last semester, and you know, we did talk about this stuff briefly in our class. I'm going to draw a line here. All right, load line, okay? I've drawn what we're calling an AC load line here. We've got IC saturation here. I'll put sat in parentheses. And we've got VCE cutoff here, okay? And if you remember, cue point. I'm going to draw my cue point. I'm going to try to get it as, this is supposed to be right in the center of this load line. But we've got a cue point here. And at that cue point, we've got a corresponding, what we're calling ICQ. That's the collector current, AC collector current. At the cue point, and we've got VCE Q. Okay, and this, I've drawn the AC load line. There's also a DC load line, very similar. They share the same cue point. Okay, so for a Class A output, let's write it down first. We can say maximum Class A output occurs when the cue point is centered on the AC load line. Okay, I'm going to flip to the next, I'm going to flip a new page here. And I'm going to draw it bigger here. So I'm going to draw a load line again. Make sure I leave myself enough room. Okay. All right, we've got a IC. VCE. Okay, we've got our load line. Let's draw it like that. That's not a very good one. It's okay though. It's not quite symmetrical. I'm going to erase that and redraw that again. Let's see if I can do a little better job drawing this thing. Okay, let's start here. That's probably a little better. All right, so we're going to put our cue point right. This is supposed to be right in the middle. just like we had on the previous slide. And what I'm going to do is I'm going to draw some line extensions here. I'm going to draw some dashed lines here, some dashed lines here. Okay. This is, we said IC sat, saturation current. Okay, this is 0 current on the IC axis. All right. I'm going to draw an extension here, dashed line extension here. Okay, this is 0 volts when it comes to VCE. And this right here is VCE cutoff. All right, I'm going to draw dashed line here, dashed line here. I'm going to draw solid line basically extending here, and a solid line extending here. We'll see if I can draw this correct now. So far it's looking pretty good, at least for my artwork. Okay, and again, this is an AC load line. All right, to get maximum swing, okay, maximum current amplitude is supposed to be symmetrical. Okay, oops, that didn't come out very good, did it? Let me redraw that again without the... All right, to get maximum positive and negative swing in my AC collector current, we want the Q point right in the middle of that load line. As that Q point shifts up and down the load line, it'll clip that AC signal. Okay, we'll look at an example of that in a minute. All right, we got the same thing going on here with VCE. Maximum. That's not looking too bad. Okay, so again, we want that Q point right smack dab in the middle. All right, and let's talk about why. The peak value, I'll write it up here. We can say the peak value of the collector current equals ICQ, and the peak value positive peak value of the collector, let's say a VCE, equals, it should be a little e, VCE Q. Okay. Actually, the output can't quite reach saturation or cutoff. Practical maximum is actually a little less than that, but it's slightly less. Let's not worry about that. Okay, but the way we've drawn it here, and I'm going to put a little star next to this, this signal is the maximum that can be obtained from a Class A amplifier. I'll put another little star on the other side. So with that Q point right in the middle of that load line, you're maximizing output for a Class A amplifier. If you shift it, if the Q point is shifted, let's draw another, let's add another page here. If I shift my Q point, all right, I'm going to draw this one a little smaller. Let's say we've got a characteristic curve here. We've got IC, we've got VCE, we got our load line, Let's put it right there. Let's stick our cue point down here. We want undistorted output. We talked about that total harmonic distortion a little bit. Okay. I'm going to draw dashed line here. Dashed line here from the cue point, and then I'll make a solid line. All right. If we're looking at, let's go back to red, the maximum undistorted signal we can have now looks something like that. We're not taking advantage of the potential amplification of the circuit. We're doing it this way. Let's draw another one here. Let's draw dashed line here. As far as IC goes, we get the same thing going on with IC. We end up with our sine wave amplitude limited by the, well, for IC it's by 0, okay? And for VCE, it's actually the saturation, the cutoff voltage. So let's see, this is VCE cutoff. Okay, this is ICQ. This is 0. This is VCEQ. And again, this is an AC load line. Okay, if the transistor is driven into cutoff, so we try to add too much amplification, let's say by a further increase in input amplitude. So we're putting too much in. Let's say we end up with something like this. I think I have enough room to draw it on this page here. We end up with something that looks kind of like this. Not kind of. This is what it looks like. I'll draw this one a little smaller. Okay. So we've got IC, we've got VCE, we've got our load line again. We've got our cue point. Let's keep our cue point low on the load line, like the one we have above here. Let's draw some usual line stuff here. Let's draw some more dashed lines. Let's draw VC cutoff. Okay. This is VCEQ. This is ICQ. Okay. We've got IC sat. I didn't draw it above, but we'll draw it here. And we've got VCE cutoff here. All right. Let's look at what happens, what our output looks like. Okay, I'm going to draw. Let's draw this here. And putting our zeros in. All right. So what's going to happen here? Now, if we look at, let's look at IC first. Okay, the positive half cycle is going to have room. Negative half cycle gets chopped off. That's called clipping. Okay, we get the same thing going on here. With ECE, positive half cycle is going to get chopped off or clipped. Negative half cycle, no problem. So we've got clipped. In both of these cases, we've got our signal clipped. that cutoff. So our output is clipped, and that means our output is going to be distorted. Okay, it's not a sine wave anymore. It's a sine wave with either the tops or the bottoms chopped off. So that's clipping. So I'm going to stop here with this particular part 1, and we'll continue with part 2 in a second video.